Okay, a very good evening to our lecturer and the faculties and my fellow friends. Today, we as a group P, we are gonna to present the topic of drug coefficient of a cube for the assignment CFD for fluid mechanics 2. Here is the content of our assignment. We consist of 4 content, which is introduction, theory, simulation of fluid CFD, and conclusion. So for the first part is introduction. Okay, firstly, I would like to introduction of our group. Our group P is actually consists of 3 members. First member as the group leader is me, Xiao Yi, and second member is Muhammad Amma, and the third member will be Nu Akira. So each of us will take some part to complete this assignment. Okay, for me, I will in charge of group P introduction, topic introduction, theory related topic, and result explaining related to theory. Okay, for Muhammad Amma, he will in charge the part of mental stimulation, explain every step clearly, and result explanation. Okay, for Nu Akira, she will in charge the explain the problem that need to be solved in CFD and geometry data and dimension. Okay, for the introduction of drag coefficient. In fluid dynamics, the drag coefficient is a dimensionless quantity that is used to quantify the drag or resistance of an object in a fluid environment, such as air or water. From hydrodynamics or aerodynamic force, the drag coefficient can be determined, as shown here. The drag coefficient Cd equal to 2Ft divided to rho u squared A. This means that the lower the drag coefficients indicates the object less aerodynamic or hydrodynamic drag. Okay, for a theory related to the drag coefficient, drag coefficients are used to calculate the hydrodynamic or aerodynamic force on an object given the density law, the speed, and the fundamental area of an object. Once knowing the drag coefficient for a certain geometry, we can calculate the force for different object size of different velocity. However, drag coefficient can vary in function of the Reynolds number, so be careful with the large extrapolation to other speed, size, or density. In typical value, a drop shape which is quite efficient can have a drag coefficient as low as 0.05, whereas a building typically has 1 above 1. Lowers mean more streamlined. So drag coefficient is particularly dependent on 2 factors on the object, which are foam drag and skin drag. Foam drag is the most important part of the object. It is the shape of the object or form of the object, and different form will cause a different drag coefficient. As shown as the right table is the table of drag coefficient of shape. The value of drag coefficient of a cube is 1.05. In this assignment, we have to stimulate drag coefficient of a cube by using the fluid CFD to obtain its drag coefficient and compare the result with the theory related. Okay, that's all for the theory part. By right, I will pass to my team member for the coming part.
In this part, I will explain the problem to be solved in this assignment. Let's take a look to the next slide. In this assignment, we have 2 objectives. The first one is to validate the drag coefficient of a cube using 3-dimensional cube. And the second one is to test the value of drag coefficient of a cube using turbulent flow. We decided to choose the turbulent flow to run the simulation in this CFD assignment. The next problem that we want to solve in this assignment, which is geometry detail and dimensions. Let's take a look with the diagram. In this assignment, we have to run the dimension one by one. We try and error. If we get wrong or we cannot simulate the axis, it means that the dimension is not suitable. So this is the last dimension that we have tried, and it can run in the simulation. The geometry details is, the first one is materials, which is we choose air. The second one is velocity inlet, which is we insert it as 2.8 meter per second. And the third one is pressure outlet, which is 0 Pascal. The dimension is, height of the huge of the biggest cube is 30 millimeter. The length is 45 millimeter, and the width is 30 millimeter.
Method in simulation. In this part, we will validate the drag coefficient of the cube using reference value in 3 dimensions. First of all, open ANSYS Fluent. Right-click on Setup and Edit, select Double Position and select Parallel. We choose 16 cores in this case. Next, import the CGNS mesh that provided. Click on Display. By selecting this and deselecting the boundary condition, you can display each zone on the screen. Check mesh and report quality. Change the turbulent model to Spallet Almaraz and choose material air. Double-click on boundary condition, select an open inlet condition. Change to velocity inlet 2.8 meter per second. Select outlet and choose pressure outlet equal to 0 Pascal. Double-click on reference value. In this case, the area in the one that directly impact the flow, which is 2 times 2 equal to 4 meter cube. The length is distance from the side of the cube that is parallel to the direction of the flow, length equal to 2 meter, and select compute from inlet, reference zone fluid. Choose method, change the shim to coupled and gradient to green gauss node base. Enable pseudo transient. Click on report definition and create new force report drag. Change name to drag 1, select cube, enable report file, report plot and print to console. Go to monitor and click residual. All numerical residual valves are 0.001. Double-click on Initialization and click on Hybrid Initialize. Click on Run Calculation and put 1200 in number of iteration and click Calculate. The simulation reached convergence at 101 iteration and drag coefficient is 1.043 is shown. Next, open Result in the workbench. Create a XY plane and choose velocity and pressure. Next, we have a look to result of simulation. The result that we get from the run solution in ANSYS are the graph scale residual and the drag 1 R plot. Based on the drag 1 R plot, we can get the value of drag coefficient of the cube, which is the peak value of the graph 1.043. Next, we also get the overall result of the process in a diagram. Based on velocity diagram, we can see the color red refer to the height velocity of the air that experienced by the cube, and the blue color is referred to the lowest velocity of the air that experienced by the cube. Based on pressure diagram, we can see that red color refer to the highest pressure that experienced by the cube at the front surface, and the blue color refer to the lowest pressure that experienced by the cube at above and below the cube.
Okay, right now I will present the conclusion of our assignment. As shown as the table of drop coefficient of shape, the real value of drop coefficient of a cube is 1.05. The drop coefficient in our simulation is 1.043. By comparison among these two data, the value is approximately the same. So a small conclusion from theory is obtained. It is a low drop coefficient implies that the streamline shape of the vehicle body is such as to enable it to move easily through the surrounding viscous air with a minimum of resistance. Conversely, a high drop coefficient is caused by poor streamlining of the body profile so that there is a high air resistance when the vehicle is in motion. Okay, I think that's all for our Group P presentation. Thank you everyone.